We're going to ask that people send in their questions via chat. That's going to be the best outcome for the most people here today. It'll avoid a free-for-all. And Jeff is going to leave his contact information at the end of the slides. So that's also a very good way for you to get in touch with Jeff to inquire about his presentation and their products. If you're really having terrible difficulties, or technical difficulties like I just did, I'm not going to be able to help you. So please back out of the presentation, go into the meeting room, I think as it's called, sorry, the main stage, and try to get help that way. I don't have any wherewithal to help you, and I really barely know how to operate the controls here. If your house is on fire, run away from your computer and dial 911. The presentation will stop around 2:15. It really depends on whether Jeff is interesting or not, and I'm going to be deciding on that, but people could also send in chat on that, and I'll take a vote. Between the next speakers, everybody should go to the main stage, take a few minutes there to look at the other products of the other exhibitors, make contacts and say hi to your old friends. As I said, this seminar will end around 2:15, and the next one will start around 2:30. Here's more for Jeff Kerr. Jeff is the Senior Technical Advisor for Engneered Assemblies, headquartered in Mississauga, Ontario. They specialize in RVRS facades. And I didn't even know what RVRS stood for until yesterday, and I'm going to keep you on the edge of your seats, and I'm not even going to tell you, but I know Jeff will tell you. Jeff has more than 20 years in the business. He actually had a stint in Vancouver about 10 years ago, and has been back in Ontario since 2012. Jeff has a very solid background in technical sales, project management, and construction and community liaison. He's got a tireless passion for matters of a technical nature in both his personal and professional life. And as for his personal life, he tells me, and please remain on mute, everybody, please. He tells me he's into winter camping. So he's those guys you see out there. No, actually, you don't see them. You don't see them out there, but guys like Jeff are winter camping. I think it's funny anyway. Without further ado, I'll turn it to Jeff. Jeff is your speaker today. And as I said, Engneered Assemblies is the sponsor of this event. So we all want to recognize and for their vital and much appreciated financial support of this conference. So thank you, Engneered Assemblies. And Jeff, we hand it over to you, sir, and thank you.
Thank you very much, Fred. Appreciate the introduction. Thank you. So what I'll do is I'm going to step over and I'm going to share my screen, because what we're going to launch into is a PowerPoint presentation. And today's presentation is going to focus on the 5 most common mistakes made in the facade industry and lead into some product launches that we have that are new to talk about. If you hear a canine stirring in the background, that's accurate. I've got a puppy in the adjacent room who's probably not happy that she's not allowed to join. Let's get started with the 5 most common mistakes made in the facade industry. I thought this was a relevant slide to start with. Some of you may recognize this. It's on top of a bridge on Queen Street as it heads into Leslieville. The river I step in is not the river I stand in. And the meaning behind this phrase is that change is always constant in life and experiences. And we know this in the construction industry. We know this in terms of matters evolving. And we certainly know this in terms of matters evolving in, well, our climate. And this is very relevant to the facade industry because, as many of you know who are in that business, facades are the infantry. They're on the front lines of all matters that deal with, as I say, the weather, the high frequency of extreme weather, climate change, what have you. And so they're a very important, a very critical point of a building in terms of wear and tear and resilience. And the need for them to be designed and installed correctly is of significant importance. So let's move forward. Engneered Assemblies, who are we? If you've not dealt with us before, as the slide suggests, we're one of Canada's most trusted facade companies. we coined the phrase uniting the house of design with the field of construction, and our passion for being able to speak both languages and bring people together in a collaborative effort to do the right thing, do the best thing for buildings possible. We definitely have a grow the whole pie mindset. Engineered Assemblies has no dreams about taking over the facade industry. There's a number of people out there who share in the facade industry with us, but together, if we work, say collaboratively, we can increase the success of lightweight, low mass, high performance facade systems, which will be better for everybody, and everyone will profit, everyone in society for that matter. So that's a little bit about Engineered Assemblies. We are a national company. While we do distribute materials, we're known very much for our design guide, which is a design guide that not only pertains to our materials, but pertains to a broad array of materials in the marketplace. A lot of our competitors' systems can be installed in the same way, and we encourage the use of the design guide to install things properly. I'll be referring to this guide within this presentation. So with that in mind, let's get rolling and start into this discussion. I thought this slide was relevant. Brawn over brains isn't the answer. Essentially, because we're going to be talking about lightweight, high performance facade systems, they are lightweight, lower mass. We don't build facades or envelopes, for that matter, with a meter of natural stone. We build them lighter weight, just like our cars these days are lighter weight and lower mass than the cars of yesteryear. And the cars of today do, as I say, manage quite well through good engineering and good design. So while they're not as big and burly and don't have as much brawn, they navigate Mother Nature certainly very well. And I like to think that Mother Nature is more than just a worthy contender. When you think you've beaten her, that's maybe when you know you've lost. So let's get started discussing a little bit about how environment is a substantial dictator. We're in an era, we've been in an era for a while where we're trying to use materials with less embodied energy. And less embodied energy means initial and recurring, and I'm going to expand on that. We're trying to design and build with higher thermal performance. And climate change is challenging our construction materials like never before. And I referred to that in the beginning in terms of facades being on the front lines of say, all the wear and tear of a building. So embodied energy, when we talk about this, initial and recurring, initial is the embodied energy it takes to fabricate a material and to get it on site. Recurring embodied energy is the energy it takes to maintain or replace that material if it fails prematurely. So what we have here is a fairly complex issue in that we're making materials lighter weight, lower mass, but we need them to last an incredibly long time. We need them to perform properly. And how do we do that? We need to engineer the way they go on buildings better. We need to design the way they go on buildings better. And that's part of this 5 most common mistakes. But not just the materials that we see, the skins, so to speak, but also the substructure that holds them. That has to be designed and engineered with an equal amount of thought because the two work in unison, okay? It's a holistic system. So, as I say, the lower mass issue is gonna come up again, but ultimately these materials that we're using, which are better for the environment and can be engineered properly, they don't hold us back from a design standpoint. So in terms of function and form, from a form standpoint, we can address historical content. We can build contemporary structures, design those structures in a way that is, I say that follows the trends of today's design. And there's no limitations there with these materials. And that goes for phenolic panels, high density fiber cement, porcelain, ceramics, some particular metals. Okay, but today's 5 that we're going to be talking about is a real issue. Now, let's be clear, the House of Design and the field of construction have equal shares in the responsibility towards this subject. Just as Engineered Assemblies has an obligation to provide clear direction towards bettering the success of these lightweight, high performance RVRS facades, and I'll expand on RVRS in a bit. But going forward, we're going to examine some key areas and show the importance of how quality is potentially compromised. And with that, we'll look at ventilation, coefficient of expansion contraction, substructure design, omissions and shortcomings, deflection limit, and inadequate shop drawings, which are a good place to start discussing the 5 common mistakes. So to begin, RVRS, what the heck is this that we keep referring to? Well, RVRS is just an acronym that Engineered Assemblies created years ago, which simply meant rear ventilated rain screen. Now, there's probably as many definitions for rain screen as there are definitions for free range chicken, okay? But with that in mind, when we look at this particular design, this is a design that was originally crafted and explained through DIN standard 18516. So Engineered Assemblies didn't invent this. This is something which was tried and true, proven, and works very well today. And it's not, there's nothing magic about this. As a good rain screen system, there's a front door and a back door, okay? We're going to manage moisture with this type of system. But one of the key areas, and looking at the first topic of our discussion, ventilation, one of the key areas is having this 1-inch cavity, uninterrupted ventilation, this active plenum. Okay, so we can see in this design here that we've got a skin on the outside in red. Then we've got a vertical girt system, 25 millimeters deep or 1 inch. And that's an uninterrupted active plenum. We're going to allow, say, ventilation run through that. It's certainly an adequate enough chamber to allow moisture to drain through the power of gravity, but more specifically, we're going to have moisture in this system, and we need to manage that more specifically with ventilation. So behind that, directly behind that plenum, we've got a weather membrane. Now with an open joint system, an open joint facade system, we want to have something like that weather membrane in there. Okay, so in this particular case, it's SRP air out shield. And this is a membrane. We're not using this as an air membrane or as a vapor membrane. It's purely here to be a secondary drainage plane. It's to stand in front of the insulation. Dry insulation works better than wet insulation, so we're going to keep it dry by having that secondary drainage plane. It can withstand a head of water. And it's also going to give us a very clear face on the inside of that plenum. Because on the outside of that plenum, on the outside meaning the skin side, we've got the back side of our facade skin. So we've got two nice smooth surfaces for air to circulate upwards, and air does move upwards. Okay, so I don't believe there can be too much ventilation for the purpose of getting rid of moisture. So with that in mind, we need that ventilation through an uninterrupted active plenum, okay, to help ventilate. And we also, amazingly enough, create a bit of a vacuum, okay? And the vacuum's gonna pull, as the air is moving upwards, it's gonna pull anywhere it can and move moisture, maybe in the form of vapor, out of that cavity. Now, this is an interesting point that engineering came up with and started speaking to me when I was talking about this presentation, that this 25 millimeter active plenum is actually a microclimate. And they were suggesting, oh yeah, this is actually interesting in that It's not the temperature on the outside of the panel. It's not the temperature on the inside of the insulation. It's its own little climate, okay? And what it helps to do, besides defer moisture and act as a great ventilation cavity, is it's also something which is going to balance temperature, okay? It's going to act as an exhaust. If we've got a hot summer day and we've got solar heat gain beating down on the panel, that air inside that plenum is going to warm up. Warm air is going to rise at a quicker rate. So that plenum is going to actually speed up, okay? And we're going to have a speedier plenum, which is going to create a greater vacuum, pulling, and we can pull moisture actually in the form of vapor through that weather membrane. So if there's any moisture within the insulation cavity that we can see here, any moisture in there whatsoever, maybe from condensation, we can actively create a vacuum to start pulling things towards there. And from a practical standpoint, say we have a lot of success. We've never had any failures with this in 12 years. So it's a very successful model, and it's a simple model. Okay, so the interesting thing about this plenum, as well as Moores and Hirschfield stepped in and said to us when we were testing our thermal substructure, and said, you know, that 1 inch of air actually gives you 0.7 of an R. So there's actually insulation value in that air. So that's got to be a plus. We've got insulation value. We've got a means to move moisture, extra moisture out of the envelope. And we've got a means to defer some of the heat energy from the face of the panel. And deferring some of that heat energy is going to be good for the panel, exhausting excessive heat. Not to mention in the summer, it's going to relieve heat from trying to transfer into the building, taxing our HVAC system, which is air conditioning at that point. Okay, so this is actually a design which found coincidentally was used in a lot of passive house models recently, having the thermally broken substructure here with the 1 inch active plenum. So a lot of passive house examples embraced this model, which was great to see. But ventilation. It's a great component. And when we talk about the 5 most common mistakes, when we talk about ventilation, this is a classic example of where flashings, which should be placed in a position, as you can see in this detail, with an exhaust chamber or an intake chamber to allow air to move in and air to move out. We look at flashing details like this, which get done on site, and this is not an exhaust. This is not an area for exhaust here. So we have mishaps like this, and maybe these things are happening in improper design, or maybe these things are purely happening in installation. But these are some common mistakes which are going to contribute significantly to the failure of a lot of panel systems out there. And as you can well imagine, looking at this, this is not a matter of expense, etc. No one's saving money by trapping and stopping the plenum. But having an open plenum and maybe installing a design with a screen like this to prevent our friends like birds or bats from making a house in that plenum, that's a great move. But we have to ensure that when we're looking at these types of systems, that when insulation goes in this particular case, it's spray foam. So it's unique, but the same thing could happen with an insulation back that wasn't contained properly. If you had that weather membrane, the weather membrane would stop back from falling forward. But in this particular case, they put the insulation in, but there's been overspray, and the overspray has come forward and blocked off that active plenum. So now we don't have proper ventilation. And when we're looking at phenolic panels or high density fiber cement, we're definitely going to see the results of that. And it's not going to be pretty. Okay. Those panels require good ventilation, and it's something they deserve. And it's neglectful to either not design this in properly or not take this into consideration when installations are done. So sloppy workmanship, okay? So that's really the first principle, and it's probably one of the biggest ones. Ventilation is key, and we see these accidents happening on site. Now, when we get into chapter 2, we start talking about dynamics of facades. We're looking at, exactly as the slide suggests, how panels react with each other and move with respect to their fastening system. Okay, so buildings are live. That's the way we build in North America. Buildings are live, they're dynamic, they move. Floor slabs move. We have steel stud construction with concrete slabs. Okay, not everything is a shear wall. So substructures expand and contract, panels expand and contract. And with that in mind, we need to ensure that these things are being taken into consideration. So with lightweight materials, low mass materials, they're going to expand and contract more than heavier weight, heavier mass, traditionally. Okay, that may not be the case for every single material, but by and large, that's the rule. So while we're trying to use these lightweight, low mass materials to lower our footprint and to do the better thing for the environment, we need to make sure that we're addressing the needs of these things, because they can work very well. And they work very well by doing things just like this, by putting in what we call fixed and floating points. So when panels are fastened to a substructure, we make sure that there is a fixed point to locate a particular panel, and floating points. And this can go for ACM, this can go for a variety of materials that have any coefficient of expansion contraction. This kind of thing must be respected, and it's not always respected. And whenever we see failures of panels, and we've gone across the country, and in some cases at the request of even some of our system partners or competitors have asked us to take a look and see why this stuff is, it's usually ventilation, fixed and floating points. It's primarily one of the two. Panels are not allowed to move. Substructures are not allowed to move properly because, as I say, our buildings are alive, our materials are alive, or they're not getting enough ventilation. We have extremes of temperature in Canada. Certainly here in Ontario, we see crazy jumps over and above the freeze-thaw line. That's going to contribute significantly to expansion contraction, but also the freeze-thaw line, as we know, presents some unique challenges for materials as well. And if there's moisture absorption and then freezing, okay, as we know, things can expand when frozen if they've absorbed moisture. So we need to consider that. The elasticity of materials, we need to think about it that way, the elasticity of materials, and make sure we're building substructures that can move, and we're going to talk about that, but more specifically, panel materials. So when we look at a picture like this, we see a fastener, it's in an over-drilled hole, which we should be doing. We put in oversized holes, okay, with rivets, or fasteners for that matter, for our floating points. So there's float between the fastener and the panel. The panel can move around. Some panels have a coefficient of expansion and contraction as much as 1 millimeter per meter. And we're talking about 4 meter long panels, 4 millimeters, things can move, okay? Well, we need to ensure that fasteners are being put in the center of holes, not on the edge of a hole, because this is a classic case that I saw at a project recently where they complained about some panels cracking, okay, where fasteners were not centered. So when this panel, when the substructure starts heading north, or the panel starts contracting, what's it going to do? It's going to provide strain right at that point, and that is where it's going to crack. And we see this in some cases where people neglect to put in their fixed and floating points on panels, and we see panel failure. In phenolic core panels, we might not see cracking, but we can see buckling, and it's just not necessary if we just follow the simple rules. And within the Engineered Assemblies Design Guide, we present this very, very clearly. So it's a very simple system to follow. Now, using rivets as opposed to thread fasteners is traditionally a more successful route, specifically because with threaded fasteners, there's the issue of the fastener tension. And that is going to be regulated by and large by the person installing it. So that becomes a very subjective point. Whereas when you're using a rivet system, especially by the model that we show within our design guide, all the fasteners, all the rivets get installed at the same tension, uniform. They're not over compressing the panel, not creating fixed points, additional fixed points. And they're all centered within their holes. So if it's meant to be a floating point, it's going to stay a floating point because we're not using a self-drilling threaded fastener and going in on an angle or hugging the outside edge of a hole, just like we see here. So fixed and floating points, coefficient of expansion contraction. Recognizing this is a key point in the success of facades. And again, this is not something that adds cost to a project, but doing this properly is going to allow facade skins to do the job they're supposed to do and last as long as they're supposed to last, not intruding, as I say, on their secondary embodied energy responsibility. So in a panel like this, as we can see, we would have maybe 2 fixed points on this size of a panel. It could be 1 fixed point when it comes to phenolics, and all the rest are floaters. So that substructure can move a little bit, expand and contract, because we typically use galvanized steel systems. Some are aluminum, but our panels are allowed to expand and contract as well. As I say, if we follow this rule, then we can create very sophisticated designs like this, and they last decades and decades and decades, 50, 60 years. In some cases with some of these materials, could be in 100 years. But we can do the edgy design that we want to do and know that from a functional standpoint, the function's going to stand behind the form, okay, and be successful. So leaping into substructure design, okay, this is a critical point because this sits hand in hand with panels and the coefficient of expansion contraction. Substructures are equally as important. The design of them and the implementation of them in terms of installation, okay? When we're looking at that, we need to respect traditional points of deflection and movement on a superstructure, okay? So if we're looking at the RVRS design or a vertical member supporting a panel, we obviously have to respect slab edges because slab edges deflect. So when we have a slab edge deflecting, that means we have to start and stop every vertical member. So that means our substructure for our system has to start and stop. Now, I've been doing this for a while now, and these are typically not elements that are included within architectural drawings. In some cases they are, but typically not. These are elements that are included in things like the Engineered Assemblies Design Guide, okay, where we talk about, say, members, substructures that are respecting the dynamics of the superstructure and how they should behave and how we compensate for that behavior. So we have the vertical members starting and stopping at these slab edges. And the same thing goes when we have a substructure starting and stopping and there's a gap, there could be movement there. Well, then we can't have a panel fastening over top of a gap in the substructure. So at a traditional point of deflection, okay, we can't have hat bars, for example, just being sistered, running in 25-foot lengths. This is definitely a case where this is benefiting installation costs. If people can show up with 25-foot long hat bars and just sister them and run them up the building, that's definitely a cost-saving measure over doing, having custom-made hat bars or custom length hat bars for that matter, being put at critical points to make sure that we're not overlapping traditional points of deflection. This takes a little bit more care. This takes a little bit of attention in terms of design, okay? And in terms of installation, respecting this. This is the kind of thing which shows up in great shop drawings. We're going to get to that point of shop drawings being critical, okay? But this is a big thing because we typically use substructures that are built out of 18 gauge material. We can't build a cage of 18 gauge material around a superstructure built with concrete slabs expected to hold steady, okay? When the superstructure starts to move, and it will, through control joints or simply natural traditional deflection, it will tear that cage apart. And what it's going to do when it tears that cage apart is it's going to tear the facade skin apart, those materials apart, okay? So we have to design accordingly and have substructures respecting traditional points of deflection, respecting the live nature of the superstructure, and having those substructures designed to meet the needs of the material in terms of their natural coefficients of expansion and contraction. So we're not going to cross over traditional points of deflection, and we're certainly not going to take a material and fasten it over top of a gap that exists within a substructure. We're going to stop it and start it. And this is a perfect example. This is a great building, 60 Richmond. This was a building done by Teeple Architecture a long time ago. It was one of the first projects done by Engineered Assemblies. And on this project, at every slab edge, there is a seam in the material. Now, I have heard some architects from time to time speaking to them on projects saying, I don't want a consistent horizontal line running across my building. Well, amazingly enough, no one has ever brought that up when looking at this building. And this is a great example of there's a horizontal seam at every slab edge, respecting the material and substructure. This building doesn't miss a beat. This building won a design award, a Canadian Architecture Design Award a few years ago. Okay, it's a fantastic looking building that's designed in a manner that addresses all the issues that we're talking about today, okay, that need to be addressed properly so it doesn't fall into one of the common mistakes, okay? So control joints, I think we've spoken about this. So with that in mind, we talked about ventilation being key. We've talked about the dynamics of facade skins. We've talked about substructures. Okay, we're going to talk about, as I say, in terms of deflection of the superstructure, of the substructure itself, L over 300. This is a big point. Having a substructure that's rigid enough in the through plane direction is never going to harm a material. Now, different materials can withstand different amounts of deflection in their substructure. For most lightweight, low mass materials, they're not going to withstand a whole lot of deflection or flexing, okay? Their elasticity is great in some respects, relatively, but if we have a solid substructure with a good deflection limit, like L over 300, we can rest assured that we're providing a good, solid backbone, or rather foundation, for these panels so as not to deflect too much. This is going to contribute significantly. And this means that when buildings are being designed and facades are being designed at the design level, that we're designing with proper substructure systems like, as we see here, omega channels, okay? So something like a hat bar, as we call it, an omega channel. And when we look at an omega channel, it has significantly more strength in the through plane than a Z bar, okay? So and this is a nominal point of expense when we're looking at designing and building a substructure. And then after design from the architectural end, engineering end, when it falls into the lap of the subtrade doing the facade installation, they're responsible for their shop drawings and engineering. They have to make sure, and we have to make sure, that poor design materials are not being implemented. And that we're using the best thing we can to provide L over 300 in terms of a deflection limit. That's going to contribute immensely to the survival of these facade skins. So they can have a great life to them and contribute immensely to our battle against the slow deterioration of the environment. We just need to use our heads, again, with that brains over brawn type of mentality. So it's an interesting point, because there used to be a time when we used to put on drawings, make good. Now, granted, this might have been 50, 60 years ago. And it was an expression that simply meant build this in a manner, in the right manner. And there was a time when people didn't need that explained to them. They knew what was the right way to do things. And we often refer to something like due diligence. Everybody's familiar with that term. And placing an obligation on people to complete work with care and requisite effort. Well, when we look at requisite, it's a thing that is necessary for the achievement of a specific end. And that specific end that we're talking about is quality construction. So if we go into this with the attitude and the mindset that we're going to do the right thing, and we're not going to design poorly, or we're not going to take shortcuts in terms of installation, then that's going to be as good as the make good component that we used to see generations ago. Okay, so, and this is something that Engineered Assemblies has thought a lot about, and hence why we're bringing out something that, say, an announcement on a new system I'm going to talk about. But as I say, if we have, failure to provide these basic elements, and we fall into these 5 common mistakes, then definitely we're going to see, as I say, costly and unnecessary tragedies in terms of our facades. This is a perfect example of some of the stuff I saw at a project recently. And of course, the subtrade will remain nameless at this point, but this was a condition where this was just above a low roof on a building. So there was a couple of roof levels on a building, and this was a low roof, and there was no access to getting onto this low roof for all intents and purposes. But what the subtrade had done with some of these panels, and these are high density fiber cement panels, or they could be phenolic, what have you, is they'd chosen certain panels and just not fastened the bottom of the panels. And they had chosen to not fasten them because from the ground over top of this low roof, you can't see the bottom of these panels. So they just ran along the front face of the building, not fastening these panels. I can't imagine what this saved in terms of cost. We're talking about maybe 1 minute per panel that we'd be spending to fasten these things in. But this is the kind of carelessness that we're seeing in some respects. And these are what we consider, this is common negligence, common mistakes that are happening in the facade industry. This is irresponsibility. Okay, so in this case, fasteners were the wrong color because from the ground, you couldn't see that. And they simply neglected to fasten the bottom of the panel. So this is like the nth degree of negligence. Now, getting into our last point here, shop drawings. This is our 5th and final component of the 5 most common mistakes. And I consider this a common mistake, not providing adequate shop drawings. Shop drawings, great shop drawings save time, save money. Great shop drawings are not cheap. They have a value to them, but regardless of their cost, the value in terms of the project is exponential, because great shop drawings are a great example to the installation crews on exactly what has to be done for this specific building with these specific materials. Meaning we're not just going to be cut and pasting common details from a manufacturer's website. We're going to be referring specifically to this building at hand and showing, in this particular case, every single panel of lightweight, low mass facade systems, every single panel that's going on the building. The location, as you can see on the bottom, of every single hat bar, the distance between them. When you have great shop drawings, there's very little room for error. I can definitely say without a doubt, there is no architect or engineer out there that would say, we don't need great shop drawings. We need great shop drawings. We need great instructions. No one likes to bring anything home to install or assemble themselves without proper instructions. And least of all, when we're designing and erecting buildings that need to last decades and decades and decades in a very challenging time vis-a-vis climate change and what have you. We need to have things done properly. So having excellent shop drawings is not a compromise. These kinds of things have to be done. So as I say, specific details showing specific conditions to the very building that's being built and the materials, okay, is critical. When we see poor shop drawings, we usually feel fairly safe that there's going to be issues on a project. Not always, but great shop drawings usually don't leave a lot of room for error. Okay, so that pretty much wraps up the 5 most common mistakes that we see. Those are the 5 most common. There's certainly more to that, but when we're looking at designing and building great facade systems, we've got these 7 factors for future-ready facades: coefficient movement of individual facade panels, joint size and fastener location, unobstructed rear ventilation, expansion gaps in vertical and horizontal framing for deflection, natural deflection, traditional deflection of a building. L over 300, we need adjustability of a substructure for misalignment of the subwall, and we need the potential to apply this all for post-disaster design requirements. If we can get these things together, then we usually have a lot of success. Now, we talked about the launch of a new product, a new system, and this all ties in very much to the 5 most common mistakes in the facade industry. So Engneered Assemblies is introducing the certified series. And the certified series, as the slide suggests, is a response to the need for transparency, due diligence, and proper installation execution of a correctly detailed, high performance, rear ventilated rain screen system. Okay. We've created the series in hopes that it'll become an industry standard. It's a means of offering a superior program of delivery, ensuring that, let's say, these system installations are conducted properly and that the facade manufacturer's warranty requirements will be met. And this is accomplished by uniting everybody with a common methodology, software platform. It's critical that people understand. I think a lot of people know this in the back of their minds, but having been in the industry for over a decade, most manufacturers' warranties are only valid when materials are installed as per manufacturer's recommendations. And this whole system came about, one, as a means of providing a certification program that ensures that materials are installed properly and done properly, but maybe more importantly for some, validating manufacturers' warranties, because there's manufacturers out there who issue warranties, and there's clients out there who believe when they receive this piece of paper of a warranty that they actually have a warranty. Let's call it 10 years, but they have a 10-year warranty, when in fact, because the system wasn't installed properly, they actually have nothing. And this is all too common in the industry. I've bounced this off, obviously, a number of people within the industry and architects, and they've reverberated the idea that it's once we get outside of that 1-year installation warranty, typically, and it's not really a warranty per se, but the installation responsibility, we're sort of left holding everything. The client is left holding everything on their own. They're under the impression that they have a warranty when they really don't. And so this series is meant to provide some structure to that and ensure. And so this is a brochure that we've put together for the certified series, and you can see in the slide that there's some common Q&A which answers some of the questions of what this is exactly, what the certified series is. Okay, and this is something that we'll be able to discuss with you. How we plan to discuss it, this is the official launch of it, but how we plan to discuss the ins and outs of the certified series is, well, if I spelled Engneered Assemblies correctly, that would be a good start. If people go to calendly.com /Jeff Kerr, we'll be offering information sessions. I'll be offering information sessions, and you'll be able to go to calendly.com /Jeff Kerr / and choose dates and go into particular times. And it'll be similar to a short lunch and learn type presentation. And we're doing this so that people can speak about maybe particular projects in private on a firm by firm basis and see if there's a synergy there for the certified series and their project. With that in mind, if a particular firm does jump into this and say, we want a presentation, for every person who attends Engineer Assemblies, in lieu of the cost of providing lunch, we're going to donate $20 per head to the local food bank for that firm. So this is how people can learn more about the certified series by, say, jumping into calendly.com and booking a presentation within the calendar. And with that, we've introduced, of course, a new design guide, a new version 2, V2, of the System 2 design guide that's become so popular over the last few years. So that's available for download off our website. We've got a few changes in it, good changes, and the system by and large has remained the same, but we have some changes in a good forward direction to help people with higher performance of their facade system. And this new V2 design guide will be part and parcel of the certified series that Engineered Assemblies is offering. So with that in mind, so we covered some of the 5 most common mistakes within the facade industry. We talked about responsibility and due diligence. We talked about a means of which Engineered Assemblies is trying to harness this issue and get it under control by offering the certified series. And say we continue to attempt to unite the House of Design with the field of construction. We've got a relationship between all parties within this industry and the environment to do the right thing. We continue to do that, and it will provide it'll provide good rewards for us. So I thank you for attending this presentation. I hope you got something out of it. You can certainly communicate with me directly if need be at jker@engineeredassemblies.com. I've got the rest of my contact information there. And with that in mind, I hand things back over to Fred and he can maybe take some questions and close us out and let you get on your day. Oh, can't hear you, Fred. Fred,
Fred, you're muted.
can't hear you. Can't hear you.
Can you hear me now?
Yes, we can.
As I was saying about myself. No, Jeff, I was saying about you. Thank you very much for that. I think your gesture about giving money to the food bank is beautiful and wonderful and refreshing, and hope that might be a great model. Jeff, we did get a bunch of questions, and I'll just say a lot of the chat was also answered by, I think, your teammates, Patrick and someone else, Mr. Gruber. So there was a lot of links to different documents that I believe people looking at the chat can pull from, and again, they can also contact you. And but we got two questions. Well, one was, Jeff, can you elaborate a little upon post-disaster design requirements, please, sir?
Well, in terms of post-disaster design requirements, usually it's a matter of buildings can be designated for say post-disaster criteria, hospitals, police stations, fire halls, et cetera, and they generally need to be built to a higher standard. It's not just those types of buildings. We did a building recently in the last few years, the data center at 45 Parliament, that was designated post-disaster. So they need to be built at a slightly higher level of performance in terms of enduring, as I say, hypothetically, wartime or earthquakes, what have you, seismic issues. And so that's essentially in a nutshell, but could elaborate more from an engineering standpoint. But usually you just need to be built to a slightly higher level, a higher tolerance of an engineering factor. Yes.
Okay, thank you. I realized, by the way, about unmuting, there's no point in telling jokes when you're muted. And when everyone else is muted, there's no point in telling jokes if they don't laugh. So that's why I was so bitter after my introduction. But Josh Bowman, you had a question. So if you would kindly unmute yourself, if you're able to, if you're still there, Josh, and ask away, please.
Yeah, I just was curious whether there's any considerations when you're installing the fixed and floating points, whether it's cold or hot weather that you're installing in. Your kind of maxes and mins and things like that.
Good question. Usually within the allowances that we allow within our design guide of the fixed and floating points, that it usually takes that into compensation. Fixed and floating points is something that they embrace in Europe as well, but largely most of the systems in Europe are aluminum based, which see a lot more expansion contraction. Respectfully, the galvanized steel systems that we use here don't enjoy as much expansion contraction. The materials still do their own thing, but that's a really good perspective of looking at things. But ultimately, if fasteners are put in the centers of holes on their float points, then they'll usually be guarded enough. There is the structural integrity of the material to fall back onto as well. But embracing this particular methodology in 12 years, Engineered Assemblies has not seen a failure when our design guide is followed. So for better or for worse, the system is working. But I respect where you're coming from because it's a valid point. Yeah.
Okay, thank you.
You know what? There aren't any other questions. If anyone, whoever jumps in first can have the next question. We'll do it that way.
Try to be so clear that there's no questions.
That's how great it was. Let me ask you then about slab deflection. So slab deflection is the slab, of course. Is it a dynamic deflection or is it just a first year deflection? Do designers ever over specify the slab deflection?
Well, that's a good question. Slab deflection, usually, in a lot of respects, people refer to just the settling of a building. Okay, but you can see some elasticity in some systems, but a lot of it isn't just the settling of a building. So the deflection that we might have to compensate for, we may not have to consider as much if we're doing, say, a retrofit 20 years after the building is built. Okay, so that let's say that traditional slab deflection, and you know what, and this is a bit of a moving target, and I'd want to defer to some of to some engineering, actually, in terms of some of the new technologies of slabs that are being designed, because there's quite a few different models of concrete slabs that are out there, and some obviously can experience a little bit more I say elasticity than others. We know very well the CN Tower is a concrete mass, and yet it sways in the wind on high windy days. So, but that's not really the same case as slab edges on buildings, but typically it refers to the initial settling of a building, yeah, which could take some time.
And well, I have another question. What do you think? I was, looking at your details, and I couldn't see them very well when my glasses were on and off. I see that you're not featuring wet seals, and I think that's part of the new generation, right? Because wet seals, of course, always stain the buildings, whether it's glass or facades or precast. Any comment upon that, Jeff?
Well, quite frankly, air vapor barrier, which, with primers and stuff like that, which I'm not sure whether that falls into traditionally the definition of a wet seal, but we don't, we're not involved in the application of that. So everything forward from the air vapor barrier is generally something we get involved in, and we try to avoid wet seals where possible. Now, in some of our details, there are the use of caulking vis-a-vis some of the window details, but that is specific to the window trade. That has nothing to do with us. Are the seals that we like to employ, or the membranes that we like to employ, are based on an overlapping system and tucking with the use of overlapping means and what have you in terms of deferring moisture. So no, wet seals are not something that we embrace. They tend to require maintenance, and they traditionally don't last the life of the building.
Mm-hmm. From it. Anyone else? Otherwise, I'm going to wrap this up. Any other questions, please? Going once, going twice, three times. Jeff, thank you very, very much. Thank you as well again to Engneered Assemblies, who sponsored this part of the this seminar and this part of it, and also were sponsored the event in general. So again, everybody is welcome to go backwards to the great hall. I've forgotten what it's called again. And there's another series of seminars, and then there's a social after that where you can get together like a good old Zoom party. So Jeff at Engneered Assembly and Jeff Kerr, thank you again, and the best of health to everybody and luck in 2021. And thank you.